In section 10.3, we're going to look at or discover some properties of logarithms. And remember, a logarithm is an exponent. Okay, definition of logarithm. Out of all these equations here, there's three of them that are true. And we're going to find the ones that are true. So let's look at the one on the left, which is the log of a product of 2 times 5. Does that equal the log of 2 times the log of 5, or the log of each thing? So we're going to test this with the calculator here. So basically if we had the log of 2 times 5 in parentheses, that's the log of 2 times 5. And what does that equal? That equals 1. So does that equal the log of 2 times the log of 5? So let's go ahead and do that. The log of 2 times the log of 5. And as you can see, we got two different things there, so that's false. So let's go back here. That one is false, so we know that's not true. Let's go down the left column here. So the log of 2 times 5, does it equal the log of 2 plus the log of 5? Let's see what happens here. If we go back to our calculator. Now, we already have the log of 2 times 5 in parentheses. That's 1. So I'm going to do, does that equal the log of 2 plus the log of 5? And as you can see, we got the same thing there as we did up on top with the log of 2 times 5 in parentheses. So that one is true. So what that's saying, and we'll define these here in a second, is this is true when I have the log of a product inside parentheses. I add the log of each individual thing together. And we'll summarize this here at the end. But let's keep going. Now, if I have the log of a sum here, the log of 100 plus 10, does that equal the log of 100 plus the log of 10? Let's go back to the calculator, and let's do the log, and then in parentheses, we're going to do 100 plus 10. We're going to hit enter. Does that equal the log of 100 plus the log of 10? So log of 100 plus log 10. And that equals 3. So as you can see, we did not get the same thing there. So that one's not true. So that's false. We know that's not true. Alright, does the log of 10 to a power inside parentheses equal the log of 10 in parentheses to that power? So let's test that bottom one on the left column there. So we're going to do the log of 10 cubed. So 10 to the third power. Okay, that's 3. Does that equal the log of 10? Now, when I do that, I'd have to do the log inside parentheses of 10, parenthesis, and then another parenthesis to enclose the log of 10, and then to the third power, and that's 1. So we can see that's not equal. We got 3 for the 1, 1 for the one on the right here, so that's false. Okay. If I have the log of a quotient, going over to the top column over here now. So we're looking at this one right here. Is that true? The log of 100 divided by 10, does that equal the log of 100 divided by the log of 10? So log of 100, oops, go back one, delete that. Oops, did that wrong too. Log of 100 divided by 10. Does that, okay, let's see what that is. That's 1. Does that equal the log of 100 divided by the log of 10? And we got 1 and then 2, so they're not equal. So that doesn't hold true. So that's false. That one's not true. Does the log of 100 divide? Now, we've already done the log of 100 divided by 10. That's right here, log of 100. So I'm just gonna do the log of 100 minus the log of 10. So I'll do log 100 minus log 10. And notice we got a 1 up there, we got a 1 there. They are equal. So this one is true. That one holds true. Now if you look at the two that have held true so far, when I had the log of, right here, of a product in here, it was the log plus the other log of each of those things. Now we're doing the opposite thing inside here. We're dividing. So when we're dividing, we subtracted the log of 100 and then minus the log of 10. So it kind of makes sense. You're kind of doing the opposite thing there. When we had a product, we added. When we had a quotient or division, we subtracted. Okay. Now that means the next one here, if you test that out, is not going to be true. We know that this right here has to be when we divide in here. So this one is going to be false. I'm not going to show that one on the calculator. Let's test the last one here. The log of 10 cubed, so the log of something to a power, does that equal 3 times the log of 10? So let's test that one out. Now, I said there are 3 that are true. And we're going to find out this one is true, but we do the log of 10 cubed. That's 3, and then we're going to do 3 times log 10. And that's 3. So those two are equal. So kind of in summary here, we know that one's true. What really happens is if you have the log of something to a power, the rule is the power goes down in front and is multiplied by the log of the base. Okay, and we're going to summarize those in this next step to define the properties of logarithms. So, if I have the log of, and inside here, I have u times v. So that is the log in base A, the base is going to stay the same, of u, and we're going to add the log of v in that same base. So if I have a product in here, this is key, I add the two logs. Now remember, a logarithm is an exponent. So when we had a product, for instance, of x squared times x to the third, we added the exponents. That's really what's being applied here, okay, because a logarithm is an exponent. If I have the log and I have a division in here, it's the log of the first thing, u, minus the log of what's being divided by, and then it's in whatever base. And this applies to any base here, so we're calling it base A. This one right here, it's the log of something to a power. The power goes down in front and becomes c times the log of u in whatever base you're dealing with. So, and this one, we don't have a rule when we're adding two things inside the parentheses for the log. So we can't do this one. This wasn't one of the properties that held true. So there's no property or rule for logarithms with that. Okay? And this is very key. This does not equal the log of u plus the log of v. Okay? When we're adding. That is, notice what we did up here, right here, when we were multiplying in there. So those are the 3 logarithm properties that we're going to be applying here as we go on in this logarithm chapter. Okay, so now, this is very key right here, this statement. When you are solving logarithmic equations, if all the terms do not have logs, reduce the equation down to a single logarithm on the side that has the logs, and then we're going to go from logarithmic form to exponential form. And this is key right here. Okay, if you notice this side right here, we're trying to solve means figure out what x is. I have the sum of 2 logs. The property says, and we're going to do the properties going either way here. The property says if I want to write this as a single log, and we're in base 2 here. Remember, these properties apply to whatever the base is. If I add the 2 logs, so if I'm adding the 2 logs, these two things I multiply. Adding 2 logs means you multiply this times this. So it's the log of x times x plus 2. Okay, and that equals 3. Now, how do I multiply a monomial x times a binomial x plus 2? I distribute. So it's really the log in base 2 of x squared plus 2x is equal to 3. Now, because it has two terms, I would suggest keeping it in parentheses there. Now, you can see you don't have a log on each side, and we'll get to those here in the next step. We don't have a log on each side, so what I want to do is I want to write in exponential form now. Here's what I mean. Remember that this base to this exponent right here, so 2 to the third power has to equal whatever's after the word log, okay, or after the log with the base, is x squared plus 2x. So when you don't have logs on both sides, there's what you're going to do. Now, 2 to the third power is 8. So 8 equals x squared plus 2x. If you look at this equation, it's quadratic. It's got x squared and x, so we need to set it equal to 0. So I'm going to subtract 8 from both sides. So 0 equals x squared plus 2x minus 8. We're going to solve by factoring. So I want factors of negative 8 that add up to positive 2. It's going to be positive 4 and negative 2. And that takes me to x plus 4. If I set this factor equal to 0, x equals negative 4. Or what makes this factor 0 would be 2. Now, you have to check these, and it's very important. Sometimes we have extraneous solutions, meaning if I plug these back in, my two answers that I get here, if I went back up to the original logarithmic equation, if I put negative 4 right in here, right in there where that x is, I'd have the log of negative 4 plus the log, and then if you put negative 4 in here, you have negative 4 plus 2, log of negative 2 equals 3. Remember what you're taking the log of. Okay, this thing right here, whatever's after the log with whatever base you're in, that can't be negative. That was one of the rules we looked at when we started defining logarithms. When that's a negative, that's an extraneous solution. It means we throw it out, kind of like we did with rational equations. So I'm going to eliminate that one because it makes, if you put it back in the original equation, you're taking the log of a negative. Now 2 will work because if I put that in, I'd be taking the log of 2 right here. And then the other one is x plus 2, so the log of 2 plus 2, log of 4. That one will work. Okay, so your only answer here, because we had to eliminate one of them, is x equals 2. Let's go over to this one. It's very similar. Again, we're adding the logs, so I'm going to multiply these. So it's going to be the log in base 2. I'm going to go ahead and multiply my x times x minus 6, which will be x squared minus 6x. And that's equal to 4. Now notice I don't have a log on the right side, so now I'm going to write in exponential form. I'm going to go this base to this power, so 2 to the 4th is equal to this answer right there. 2 to the 4th is 16. So there's what we have. I'm going to set equal to 0, so I'm going to subtract 16. So x squared minus 6x minus 16. And I'm going to factor. Factors of negative 16 that add up to negative 6. I got to have one of each sign. So it'd be negative 8, positive 2. Which means if I look at what makes these factors 0, zero product property, x equals 8, x equals negative 2. Now we got to check, are any of them extraneous? And notice we had an x right there. So if I put negative 2 in right there, I'd be taking the log of a negative. Got to throw it out. Okay, and we'd also be, if we put negative 2 in there, we'd be taking the log of a negative there. But if it makes a negative log, or taking the log of a negative anywhere, we got to throw it out. 8 would work because we'd be taking the log of 8 and the log of 2. So that one does work. So our only answer, is that one right there, x equals 8. There is a possibility you could get an answer and then you have to throw it out, so it could be a no solution. Always check for extraneous. here's the next rule. If all the terms do have logs, then get a log down to a single log on each side, and then you can drop the logs and solve the remaining equation. And we'll look at some examples here. Now notice I only have one logarithm on this side, but over here I have two logs. So I'm going to keep the left side the same way, or what it is. Here, what's my rule? If I'm adding logs, I multiply those two things. So this will be the log in base 4 of 15. Now, there's not really two terms, but you can keep it in parentheses. Here's the difference. On the last couple problems, we didn't have a log on each side, so we had to write an exponential form, meaning the base to the power over on the other side equals that. Here, notice I got logs on both sides. You can just drop the logs, cross them out, which you can't do if you don't have a log on each side. So I take this, 3x plus 2, and that equals 15. Now I just solve for x, so I subtract 2. So 3x is 13, divided by 3, and I'm going to leave it as an improper fraction. It'd be 13 thirds. And if you plug that back in, the only place you have an x is right here, 13 thirds, which is 4 and 1/3 or whatever, times 3 plus 2. That would make a positive right here, so we'd be taking the log of a positive. So that one does check out. That means that it's not extraneous, and that would be our answer. So you can get fraction answers. All right, let's go to the next one. Notice I've got all terms with logs. Here's what I want you to notice. We've got something multiplied by a log right here. So what you need to do with that is that becomes the power on x. So I move that up, and I'm taking the log of x to the 4th. It's the rule. Remember, one of the rules was we had the log of something to a power. The power comes down in front. Well, now we're going in the reverse order. If we have something times the log, that becomes the power. Okay, because I don't want to have a number out in front. That should always be your first check. And then I have minus the log in base 2 of 5 equals the log in base 2 of 125. I'm subtracting, which means I'm going to write this side as a single log in our base 2 that we're in. That means I divide these two because I'm subtracting. I don't multiply them. So I have x to the 4th divided by 5 equals the log in base 2 of 125. Now I got a log on each side, down to a single log on each side. Now I can drop the logs. So I have x to the 4th divided by 5 equals 125. So let's get rid of dividing by 5. Let's multiply both sides by 5. So I have x to the 4th equals 125 times 5, use your calculator, is 625. So now I want to take the 4th root of 625. Notice it's an even root, so I need a positive and negative. We've done some other things dealing with positive and negative roots, and 625, the 4th root, if you do that on your calculator, is 5. So it's positive and negative 5. Now we got to check. We have a positive 5 and a negative 5. Notice the only place I have an x is right here. If I went and put negative 5 in there, I'd be taking the log of a negative. So negative 5 is extraneous. So we're going to throw out the negative 5 because it comes up with taking the log of a negative in our original logarithmic equation. So only 5 works. Okay, sometimes you might get both of them to work. All right. And I'm going to stop the first part of this lesson. We got a few more examples to look at, but that'll be in the second part here.